Well, thank you all for joining today for our Innovations in BMS Testing Part 1 presentation. We're going to be doing a fireside chat today with two exciting guests that I'm really excited to present. So we'll be talking about the importance of BMS testing today, from EVs to grid storage. So I guess just quickly to introduce OPAL-RT Technologies. So we're a hardware and software company that's been around for over 25 years. We have the mission of empowering engineers and scientists around the world with real-time simulation technology. Our history has been really more in the power systems side, but we are also very, very strong in power electronics because of our FPGA simulation, our high-performance FPGA algorithms that we've developed. And through that, we felt that we could serve automotive and aerospace customers best through that knowledge. So we have offices pretty much all around the world, over 400 employees, and yeah. So I will let our speakers introduce themselves. So we have two exciting speakers. Our first one is Dr. Oindrilla Dutta from Sandia National Labs. I will let her give a quick intro.
Hello, everyone. I'm glad you all could join us. I'm Oindrilla from Sandia National Labs. I'm a senior member of technical staff in the Energy Storage Technology and Systems group. My group has four major thrust areas. One is energy storage, where we build new electrochemical cells and perform battery abuse testing. We have power electronics, where we build new devices, wide bandgap devices, and as well as build power electronics hardware and control software for existing as well as new topologies. We have analytics for power system modeling and optimization. And finally, we have demonstration group thrust area. I am in the power electronics thrust area. I work on the development of system integration, hardware and software platforms for grid-scale energy storage systems. Thank you.
Thank you, Angela. And we also have Dr. Guenter Prochart from Virtual Vehicle. As long as we can hear him, I would like him to introduce himself.
So maybe I start over again. My name is Guenter Prochart. I'm with Virtual Vehicle Research. It's an RTO, a research and technology organization, which means it's a non-profit organization doing research. And we have a bridging function between universities and industry. We are approximately 300 researchers. And as our name implies, virtual vehicle, we are on the simulation side, doing simulation and digital twinning, of course, in order to reduce the time to market, to reduce costs, to increase the quality, to increase safety. And our focus is, as you can see on the right side, it's green mobility, transport, validation and homologation, automatic driving, safety and security in the field of automotive and rail up to now. But we have now some new domains, for example, aviation, and especially these new eVTOLs, this electric vertical takeoff and landing vehicles and aircrafts of interest for us. And of course, we are not fully virtual. We have, in order to close the feedback loop to reality, in order to verify all your simulations, you need to have also some real world measurements. You need to do some real world measurements, and we have a lot of test beds, like you can see here, for example, NVH and powertrain test beds, as well as battery test beds. So I'm in the battery group. And we are doing funding projects, but also service engineering services, and we are, at least in our spot and with German OEMs, we are quite famous on doing thermal runaway tests in our lab, which is called the Bat Cave. and yeah, I'm glad, and thanks again for having me. I'm glad to be here. My personal experience is I'm now 15 years in e-mobility. I started with test system, working on product development for test systems, so meaning traction battery testers and traction battery emulators. So that is some kind of power hill because it mimics or it emulates a real battery in order to test the inverter and the e-motor. And that was in my former company, and now I'm with Virtual Vehicle. I'm working on power and components, so meaning not only the battery but also the electrified powertrain inverters, the e-motor, but of course the battery, and of course. Therefore, I'm here. Also, a big topic for me. It's the BMS and the BMS testing. So, thank you again.
Yeah, of course. And I guess just to kick things off, I think that's a great introduction to kick things off. I guess just to introduce myself really briefly, I'm a go-to-market manager at OPAL-RT Technologies. I focus on e-mobility. So, I'm learning a lot from Oindrilla during some of these prep sessions that we've had, and we're really excited to kind of have this informal chat with you all about some of the topics that I've listed here. So I guess just to kick off the subject, just to kick off the conversation, we know that to reduce carbon emissions, with the objective of reducing carbon emissions, our governments are really pouring a lot of money into incentivizing EV adoption. And we know that one of the limiting factors in EV adoption is the battery, because it's the most expensive part of the vehicle. And it really is, like, there's so many topics surrounding the battery. And I guess from an e-mobility perspective, and this question is for you, Guenter, what are you seeing as battery technology trends?
Well, I guess everyone here, also the listeners, are quite familiar with the trends currently going on, or at least all of us know that there's so much going on in e-mobility now with the different battery technologies. So currently we are having the generation 3A and 3B batteries with the different anode material, carbon and silicon for 3A and 3B respectively. And now it's time to go for the solid state battery with the lithium anode. And this will be the next milestone, so to say, because it really will increase the energy density and the capacity of the batteries, and will somehow tackle all these questions many people have because of range anxiety. And therefore this is one important step, so to say. And of course it's going beyond that. The generation 4, it's also at least in under consideration with the lithium air battery. And so it's quite a long quite something going on in this research area of the battery technologies. And of course that will bring some new requirements also for the BMS as well as for the BMS testing side.
Yeah, for sure. And I mean, I know that for solid state, there's a lot of concerns for safety, right? Like, I guess what's different about the solid state battery than I guess the Gen 3 or previous generations?
Yes. So that's true. I mean, there is a lot of there are already some videos out there showing some, for example, thermal runaway, some nail penetration tests with the solid state, with some early solid state prototypes, and they seem from safety perspective, they seem so to say safer,
Okay.
but let's see. I mean, we had a few weeks ago, we had not really a full solid state. It's in between solid state and the generation 3 battery, and this still shows the same results on the nail penetration as the generation 3 batteries. So I'm very curious to have one in our lab, in our bat cave, to do some thermal runaway tests on it.
Okay, and I guess, are there any other trends that you're observing with battery technology from an e-mobility perspective?
Yeah, there are a lot of trends. I mean, we have. So, for example, or if we go to the topic itself, what will it change also for the battery test systems? Of course, everyone is trying to design a technology agnostic BMS, but I guess that is a little far ahead, because for these new battery technologies, we will need new battery models. And so, for example, the current battery generation 3, the lithium ion batteries, they feel quite well at room temperature. So at 20-25 degrees, they perform best. If you go below that temperature, or above the temperature, it will affect the aging of the battery, or it will affect the performance of the battery. So on one hand, on the other hand, the solid state battery are different. They have a different temperature range. So, for example, they are performing well at 60 degrees, for example. And
Okay.
this reflects also in the state of X algorithms, because not everything is linear. So there are some linearities in there where you have to also see that the temperatures in it, and so this will be also needed to be reflected on the battery models as well.
Mm-hmm. Yeah, absolutely. And
Yeah,
I
of
think
course, I have
you touched on a
yeah,
lot of different
I have of course a
topics
lot.
as well. I think
I
there's a
have
bit
I
of a
have
lag.
I have a lot of topics, so maybe I can just mention then, because it's worth mentioning, because it reflects the BMS testing. So of course, we will see additional sensors.
Mm-hmm.
For example, for safety reasons, you will include gas sensors to pre-predict the thermal runaway. You will have additional sensors like eyes, like the electrical impedance spectroscopy, to increase for example, the state of health predictions.
Mm-hmm.
And of course, there are some trends in the battery pack, so it will be more modular. Uh, uh, in that sense, that there is also some thoughts about having a basic battery pack permanently in your EV, which serves your daily average range. But if you go, for example, on a longer trip, on a business trip, on vacation or whatever, you will go to your workshop and they will install you an additional and extended battery pack. And
Yeah,
this is,
so
of
like
course, I mean, it sounds easy, but this is also a topic of the BMS. The BMS has to handle that. So if you have an additional and extended pack, the batteries management system needs to handle that. And as well, if we think on the BMS test system, it needs also to handle that. Then, of course, you
yeah.
have additional battery pack topologies. So cell to pack is a topic, cell to chassis, cell to body, and yeah, this is also a complete new situation, because up to now you have the cells and the modules, and the modules you're forming a pack out of them, but this has also some change in topology of the BMS, and the
Yeah.
BMS test system needs to handle that as well.
I guess all to increase kind of this modularity aspect, to be able to kind of
Yeah,
swap
yeah, yeah,
out,
yeah,
to make it easier. I guess easier for charging. So easier for charging purposes, maybe for enabling faster charging, and also for, as you
yeah,
said, range.
yeah,
So range anxiety. So I think there's a lot of different solutions, I guess, or different topics that are being
And
investigated.
it goes I need to mention two additional points because they are
Mhm.
also very important. Of course, you will see different communication technologies. So, for example, the communication of module controllers to the main BMS could be done not only wired but in optical with optical transmission, or what is now also a major trend, wireless BMS.
Mm.
And it's currently available also with a standard frequency range of 2.4 gigahertz, but the new systems will also go on wideband communication, so meaning above above 5 gigahertz. And with that, you have different situations within the battery. So, for example, you have then you need this also is reflecting when you have. So that is one point. The other point is that, of course, new materials will come in, lighter materials, new materials for cooling, this phase change materials, then plastic instead of metal, and then you have a topic with the wireless communication, for example, on this wireless BMS, because then you don't have any longer a Faraday cage
Mm.
if you are not using metal, and then you can have distortions from outside, distortions from inside of the battery because of different materials. So this is quite some challenge. So we are currently also working in different projects on the topic.
Yeah, I've heard
And
also
last not least, then
I've heard also the concern of cybersecurity comes up as well, of that
of
being an
course,
issue.
as well, if you have if this with this wireless communication, you have so to say an entry point for hacking the systems, for hacking the system, and this is also, of course, a big topic.
Yeah,
And
for
last not
sure.
least, I would like to mention, because I've now talked quite a lot, uh, increased complexity. So meaning that there is you need up to now, up to a few years ago, it was only the electric vehicle, and you have or you have only seen the vehicle, but up now we need really a holistic view, because it's with e-mobility, because of vehicle to grid, vehicle to home possibilities. So not only that you charge your battery, but you can also feed back to the grid. And this
Mhm.
is of course increasing complexity and increasing communication. So the BMS needs to have some data, some information also from the cloud, from the environment, and so on, from the grid, of course, to it,
Yeah,
from that side. And yeah, and then of course, if you see the full life cycle of the battery, you have this, we need also to deal with this transition from first life applications. So meaning
yeah,
if the battery is at this end of the lifetime within the car, and you can then go to second life application and use it in this in stationary applications.
so
That is also some complexity we need to handle, because there also the BMS, on one hand you can use the full back, or on the other hand you can use at least models
yeah,
and use them to build up new bags for the stationary applications. Yeah, that would
for
be
sure.
also one factor. So the increasing
And I think,
complexity, and I guess that is
yeah,
a good point to make a hand over to the grid, because
yeah,
vehicle to grid and vehicle to
I was
home,
gonna
it's the
say,
perfect fit
yeah, I was gonna
to hand
say, I guess
to
there's
go on the other topic to the grid side.
right, exactly. I guess also with the rise of alternative energy sources, there's like this growing need for energy storage. But as you said, I think a big driving factor is also this idea of extending the life of a battery, right? Because it's only usable up to a certain point in an EV. I think it's
Yeah.
like at 70% of its life, uh, so So I guess, Oindrilla, this is a great, I guess, opening for you. What battery technology trends are you seeing on the grid side?
So some of the trends are common to e-mobility and some of the trends are unique. So one of the unique trends is that it comes from the applications that are required for the grid. These applications have widely varying requirements for duration of operation, ramp rate, energy density, power density, and number of cycles per day. So, so far market drivers exist for short duration and medium duration. An example of short duration would be frequency regulation, and medium duration would be peak shaving. So market drivers exist for these applications. And we are gradually seeing a trend towards long duration storage, which is greater than 4 hours. And the applications are intraday renewable support or seasonal grid support. And DOE is also pushing towards long duration storage. And one of the main challenges of long duration is that lithium ion cannot do it. Lithium ion cannot operate for greater than 4 hours because they degrade really fast. If you go for a depth of discharge beyond a certain value, they will degrade really fast and catch fire. So there is this requirement for newer chemistries, such as zinc-based chemistries, zinc oxide, zinc manganese, sodium-based chemistries like sodium sulfur, or metal air. And because the grid applications the requirements for these applications are so widely varying, a single chemistry cannot perform optimally in all the aspects of generation, transmission, and distribution. So there is also a requirement to have hybrid systems. Instead of having a single stack of cells, there's a requirement to have multiple stack of cells. In each stack, you'll have cells of same chemistry and similar state of health, such as, let's say in one stack, you have lithium ion and maybe second life recycled from the EVs. And in another stack, you have sodium sulfur and maybe they're new. So these are different. You need hybridized stacks, hybrid battery systems for the grid. Like Guenter mentioned, there is the need for modularity there because there's a large scale installation. You should be able to hot swap a stack when something goes wrong. Otherwise, you have to shut down entire operation and stop supplying the load. So there's a need for modularity. There is a huge need for cybersecurity, and cybersecurity so far had been an afterthought, but nowadays people are taking it so seriously because there have been cyber attacks on the grid. Yeah.
Yeah, and you were saying with the different chemistries, I mean, that brings a need, and Guenter mentioned this as well, but that brings a need for a lot of different sensors or a lot of different types of data because they're not the same. They're not the same. And can you describe, I guess, some of the differences that you see with the different chemistries?
Yeah, sure. So most of the off-the-shelf components that you can buy for testing batteries are designed for lithium ion. So any BMS will have voltage, current, and temperature sensors. And the models, like the equivalent circuit models, are meant for lithium ion. However, with other chemistries, you need additional sensors like gas sensors to identify off-gassing, which will tell you if there is any side reactions taking place. And that happens I personally have seen that happening in zinc oxide cells. Then there is a need for pH sensors, pressure sensors. So some cells, some certain chemistries, their performance changes when pressure increases. And there is also volumetric expansion of the cells and due to the reactions taking place. So there's this need for pressure sensors. And it has become so crucial to identify battery degradation. And that's why there's a need for impedance spectroscopy, where you can identify the impedance, internal impedance of the cell, and predict its degradation over time. This also, and also there is a need for at least for grid, it's a huge thing, because these are very large scale installation. There are hundreds of cells in series and parallel. So when one cell catches fire, the fire quickly spreads throughout the entire installation and shuts down the entire operation. So there is need for identifying and arresting thermal runaway. So when one cell catches fire, you should be able to isolate that fire into limited number of cells so that your entire installation doesn't have to be shut down.
No, that's super interesting. I know we have some questions in the Q&A section that there's one question specifically related to state of battery health estimation. So someone said, I'm doing my master's tech project on state of battery health estimation. My question is that, can you tell me what would be the best method for reducing the aging effect of lithium-ion batteries according to the recent research? Now, I know this is probably a long answer, but I don't know if there's something that you can give as a tip for this question.
I would say EIS. So get EIS data, put it in the lithium-ion models. There are some newer models, such as single particle models these days, which is different from the traditional equivalent circuit models. So look at newer modeling techniques, do EIS measurements, put it in the model and calculate. There are algorithms. You can fine tune those to your need, or you can use the existing ones.
Okay, great. Thank you. And then there's a question for Dr. Guenter. So what are the challenges for EIS tests for the battery pack level versus battery cell level?
Yeah, that is that is a very good question. It's a question. It's related to the interpretation. So if you do, which has been done quite some time up to now, that you doing ice on the cell level, you can really tell what's going on this particular cell. But normally in a battery pack setup, you are using one ice sensor from different manufacturers. They are now available out, and you're doing that. You're applying that to a module, and then it's of course you need to interpret this data, so you don't see the impedance not only from the cell but from the whole module, and you need to interpret that in the proper way. I mean, it's easy when you're doing that, when it's really one cell is completely going out of range, but related to the aging effects, to, for example, it increases the inner resistance. But if that is gradually done over different cells, it's not so easy to interpret. So that is the big difference, and these are the main focus now in some research, or in I guess in many research projects, that how can you interpret that you have this impedance value from the whole module, not on a particular cell, because on a particular cell it's quite easy to know what's going on in the cell, so to know the aging, because you know the inner resistance and so on, but it's not that easy to interpret it on the module level. So that is the big difference, and that is the challenge. That's a great challenge.
Yeah, that sounds like it.
If the person who asked the question has already some good results, please share it with me, because we are currently working on it, and it's not that easy. It's not, to our point of view, it's not that easy to have that proper interpretation of this common ice value which you get from the module.
Yeah, we have another question that's related to what Oindrilla was talking about, about the hybrid battery packs with different chemistries.
Mhm.
So the question is, if the aging speed of one chemistry would be faster or different compared to the other parts, how can that be addressed?
Yeah, so it's not just the aging that that varies between chemistries. There are a few key factors that need to be taken care of to maintain the state of health. One is the operating voltage range, which changes from one chemistry to another, and that voltage range varies as the cells age, and that variation is not linear. Another thing is how you cycle a cell. For instance, with lithium ion, you would do constant current followed by constant voltage. For alkaline cells, you will do constant current rest, constant current rest. For another chemistry, you will do constant current followed by constant voltage followed by float. So there are these different operations. And the way to handle this in a hybrid system is to make it modular. So current state of the art is not modular. You have battery stacks all connected together to a single DC-AC converter. So you do not have individualized control on each stack. Hence, you must introduce a DC-DC converter with each stack, and these DC-DC converters on the low voltage side will be connected to your battery stack of a particular chemistry and state of health. And on the other side, they will either connect in series or parallel to the point of common coupling of a DC-AC converter. So once you have these DC-DC interfaces, then you can have dedicated controls for each battery stack, and you can handle all the variations, the voltage range, the cycling protocols, and how they degrade over time, so that you can change your control actions looking at their degradation. Another advantage of this topology is pulse testing, which is used to test the quality of the cells. So as of now, if you have to check the quality of a cell, you'll have to shut down operation and do it and check the cells in a stack. But if you have these DC-DC converters and multiple stacks, then you can have, let's say you have 4 stacks. You can have 3 stacks applying the load where while you are doing pulse test on one stack. And this also helps you in hot swapping and arresting thermal runaway. So if something goes wrong in one stack, one cell catches fire, then your DC-DC converter can disconnect that particular stack from the rest of the system. And your operation is still uninterrupted because you have other battery stacks in the system. So it helps you in hot swapping and arresting thermal runaway as well.
It sounds really complex, and I think that, that shows the need. And, this is my Opal spin on this, but that shows the need for Hill testing. And, I know there's a lot of questions related to Hill in the chat. But I think with all of these test requirements across all of these different industries, we are seeing the need to have more and more testing as early as possible in the cycle, in the development cycle, to reduce risk. So I think, this is where OPAL-RT can help. Our different sessions will be talking about specifically BMS Hill and our virtualization technology that we have for testing BMS. So I really encourage all of you that have Hill questions or P-Hill questions or everything like that to come to our next sessions, because that is really going to be the focus for the next sessions.
Yes. Maybe I can add something to that.
Yeah.
Because it also answers the question, one of the key question, why is BMS testing so critical or so important? Because of this, because of these new trends, of this new technology, and as you were mentioning, the BMS is the central function also for the safety to guarantee the safety operation of the battery of the battery pack. And therefore, when you have a lot of different a lot of new topologies, new modularity, additional sensors, new battery technologies and so on, it's really necessary at first and foremost from safety for safety reasons to test as early as possible and to test as much as possible.
Yeah, exactly. And we are seeing a trend towards as virtual. I know I have a quick, let me just show it really quickly, but I know what we've observed, I guess, in hill as hill trends, if you will, is that we are seeing the need to test as early as possible. So as close to pure software testing as possible. But at the same time, we're seeing a need to test as close to pure physical as possible. So it's kind of, we're seeing a variety depending on the needs of tackling at different points in the development cycle. And the idea for the BMS Hill solution that we offer at Opal is that we are really trying to tackle and to help our users go from pure software testing to pure physical testing.
Yeah.
Now, I guess just to get back to the
this is but just one moment.
yeah,
That is a very
yeah,
important point. If you stay on this slide,
yeah, sure.
it's for me it's maybe not it's a subgroup, maybe not a main group, but a subgroup in there, a step in between there where you test on protocol level. So meaning because
Yes.
of this new different communication technologies, for example, if you have a wireless BMS with the different materials, you have different reflections, you have different you can have if you don't have any longer, or if you also include in the battery housing not full metal but also plastics out of weight
Mhm.
and cost reduction, you will also see some distortions from the outside. So from the car environment, so to say, and this is also, for example, you can then this will influence your error bit rate, and this you need also to handle that. And this is something which you
Absolutely.
can really test on the protocol level. So meaning you have not the physical values. So for example, not the cell or the module voltages and temperatures, but you have the physical transmission from the module controller to the main BMS controller, for example,
Mm-hmm.
where you really have the physical transition, and you can then have a more extensive fault insertion. You can look what happens if the signal goes down, if the signal
Like goes dark or yeah.
goes down, if the bit error rate increases, if the signal
Mm-hmm.
quality goes down, and something like that. So for me, that is also quite
For
what
sure.
we are seeing with our customers and in our projects, that this is also a valuable step
Yeah,
now and
absolutely.
also in the future, when it comes to that all these different communication technologies will come into play on the one hand, and on the other hand you have much more communication because of this new increased complexity with vehicle to grid, vehicle to home, and so on.
Absolutely. So we do have a ton of questions in the chat that I do want to get to. So I'm going to go back to this slide really quickly. Let me just take a look here. So I think based on the question that was asked before, so that on the grid side for energy storage, we're seeing a lot of different types of chemistries all in the same system, right? But there's a question here that's related to EV. So do we or can we use different types of batteries in an EV, like an existing car, like lithium ion and lead acid combinations? What are the challenges? I guess this is the question for Guenter.
Yeah. So that is not so easy to answer. So it first on the first perspective, it's easy to answer because normally the battery packs nowadays, they have only one chemistry in there because of manufacturing because of cooling. Of course, you need to have a thermal conditioning system within the battery pack, and because of that, you have not only one chemistry but also one cell type. So meaning cylindrical, pouch, or prismatic cells. So, for example, if you go for cylindrical cells, you can have a very effective cooling where you have a coolant around the cylindric cell, so to say. And so that is quite hard if you really mix that up. But as I mentioned earlier, if you have that more a modular pack system, for example, if the basic pack is a fixed topology, a pack which is permanently installed in the EV, and you would exchange or increase the range of it, and you go to your workshop and it's another pack is installed, that is of course possible that this pack can have a different chemistry, but this of course will increase of course the complexity also to the BMS, because different chemistry, you have different approaches of the SOX algorithms. You need to handle that. You need to handle maybe different cooling, because this one, it has this thermal conditioning. The other chemistry has another thermal conditioning system. So basically, up to now, I would say no. So it's again out of manufacturing. It's very common that you have one, or it's definitely so that you have one chemistry within one pack, even one form factor within one pack. But
will
in
also
future,
make the system bulky, right? If you have multiple chemistries, just the control and the circuitry will be too bulky for an EV.
But I would say it could be possible if you have that modular approach. So I would not completely say it's not possible, and it's not meaningful in the future. So
for trains, for instance, they do a hybrid of battery and supercapacitor. The supercapacitor helps during acceleration and capturing the regenerative braking energy during deceleration. So one high energy density, another high power density chemistries have been hybridized for train applications. Like,
No, I mean, that's really interesting. So again, we have a lot of different questions. I don't think we're going to have time to answer them all, but there are a few that seem quite interesting. Well, I guess first there's a call out to Oindrilla. So thank you, Oindrilla, for underlying all these critical points. I'm a PhD student, part of a research group at Illinois Institute of Technology, ECE department, that exactly tackles these points. So that's cool. Thank you for that feedback.
Thank you.
So I think the next question that I think we could answer is, so this question is to both. So how is, sorry, I'm just trying to get through it. So how is the cybersecurity of battery energy storage system ensured in a real world? And what are the industrial practices in your labs?
They're not yet ensured.
Okay.
They are still at research stage.
Yeah.
The things that we are trying to investigate, and I wouldn't say it's a developed technology already. It's still in research TRL, if you call it. So is one thing, the primary thing is intrusion detection. And it's not easy for batteries. So for instance, when you are getting battery measurements, some measurements could be fault of the sensors, some anomalous measurements, or some could be intrusion. And it's very difficult to differentiate between them. And there is heavy research going on in that area. I don't have an answer to that exact question. No, the answer is no, it's not ready yet.
Well, I'm seeing the same thing on the I guess on the hillside. You know, what I've been reading is that it's kind of a couple of years out still. This idea of kind of keeping everything wireless, but it sounds like, as you said, it's really top of mind, and there are obviously so many other challenges that are kind of urgent and high priority, like safety, safety
Yeah.
concerns, like trying to minimize the risk of fire. And I know both of you were joking about the cost of insurance, or like trying to get
Yeah.
insurance. So,
Right.
things like that seem a bit more urgent than
Yeah. Like practical challenges.
yeah.
No one wants to give you insurance.
Exactly. Okay. Let's see if there's any other. I mean, if you both also want to open up the Q&A, if there's any question that calls to you specifically, I think we have time maybe for one more before we close out the session.
There is one question which I think both Guenter and I should answer, and also Nadine. So, are the Hill platform's battery models detailed enough and provided enough data for BMS testing? What is the critical data, Guenter? Is Guenter there?
Sorry.
So I guess
Can
I
can
could, yeah,
Oh,
so
yeah.
we're
can you
answering the
repeat it?
question, are the Hill platform's battery models detailed enough and provide enough data for BMS testing? What is the critical data? The
That
big
is a
question.
no. That is a very good question, and I don't know. To answer that, you can say, of course, it depends on the library which is provided by the BMS supplier, or by the Hill supplier. Maybe Nadine, you can tell it for OPAL-RT.
Yeah.
Yeah.
But of course, it depends on also on what you are focusing, because there was one question about the SOH, about the SOH algorithms, and if you think about that, you have a lot of possibilities to do the SOH. For example, we already mentioned the direct version would be OCV and open circuit voltage, or ICE. Then you have a model-based with modules like electrochemical or equivalent circuit. Then you have adaptive filtering like Kalman filters. But then you have for example, the data-driven approach. So with fuzzy logic, with artificial intelligence, with AI. And if you go, and it fully depends what is your aim, what will you do. So, and what algorithms you're really focusing on. So for example, if you go for the data-driven approach, you need a lot of data, and you need the right data, so to say. If you can you really, so if you just record the data out of a fleet, for example, of some cars, is it really enough, or you really need to have a closer look at the data? For example, if you are on the traffic light, and the car is standing, is that to include, is it not to include, or something like that? It's a longer topic, but so the story is that always it depends.
Yeah.
So it depends on, so basically what is my expectation, and we are working together with OPAL-RT
Yes.
on some of that, on the ICE topic, that you have a good basic model which you can start from. But of course, depending on your research focus, depending on your topology, depending on your algorithm, you need to extend it, you need to measure, you need to get data, you need
Yes.
to feed it in, and stuff like that. So it's not an easy answer, I'm sorry.
It's not an easy answer, and it's not an easy subject. So we know that characterizing the battery model is one of the trickiest parts right now. So I guess on our end, on the Hill side, what we aim to do is work with external organizations to help you do that. I don't think at Opal we are experts on that for sure, but our hill system can adapt, I guess, to changing requirements. So if there's different battery models to import, it's flexible or it's agnostic to that. And then we can work with our users. Really, we serve our users for if they have different sensor needs or different parameter needs. So you know, our hill can adapt to that. We're trying to make it generic enough to adapt to all those changing requirements. And I guess, Oindrilla, is there anything on your end that you wanted to add to that?
I think data is very important. And at Sandia, we have these initiatives of collecting different data from all our different experiments, and also external entities can upload their data. We have a website called Battery Archive, which is open source, and it has data available from abuse testing experiments and from researchers as well as Sandia. And we try to also upload more data as well as other people. So if you're looking for data for modeling, then definitely look into Battery Archive.
Cool. I didn't even know about that. That's awesome.
Yeah.
Okay, so I think that's pretty much it for the questions for today. So just thank you both so much for being a part of this. Really appreciate that, and thank you to our attendees for all these questions. It's great to see so much interest and so much discussion. I really love that.
Yeah, maybe I can add I can add something. If
sure.
anyone out there, anyone who is listening is interesting, please contact me. You can find my email on the web. So if you are interested in one of these topics in BMS testing, in battery modeling, in abuse testing, in aging testing, in EV powertrain simulation, please send me an email.
For sure. Yeah, so you have the names right here of our speakers. They're available on LinkedIn. You can go check them out.
Thank you,
yeah,
Nadine. You ran a great session. Yeah.
So I guess just to let you know of our upcoming schedule, we do have part 2 and part 3 that are going to be really talking more about the hillside. So part 2 is going to be with Comemzo, our partner that makes battery cell emulators. So, and you know, they're real experts on this topic. So we're very excited to have them at the beginning of June for part 2. And then part 3 will be discussing some emulation technology that Opal has created on FPGA to add on to your BMS hill to help you get closer to pure physical or pure software testing. So I think that's pretty much it for the upcoming webinars. Thank you so much to all of our attendees again, and we'll see you soon.
Thank you. Have a good day. Bye.
Thank you very much. Thank you. Bye-bye.